حضورنا الكريم. من منطلق دور إدارة الدعم الفني لتقديم ورش تثقيفية لمنتسبي جامعة الكويت لمواكبة التطور التكنولوجي ومتابعة المستجدات في مجال تقنية المعلومات فيما يخص البرامج العامة والتخصصية التي تشرف عليها الإدارة، حيث تم تنسيق ورش أونلاين وويبنار بالتعاون مع الشركات العالمية ذات العلاقة. واليوم يسر إدارة الدعم الفني أن تستضيف شركة سمارت فيجن لتقديم أولى ورش العمل الحضورية بعنوان AI Spss. فليتفضل السيد محمد زهدي لتقديم الورشة.
أولاً بشكركم على الحضور. احنا مع جامعة الكويت. بشكركم على الحضور. وجامعة الكويت مش حد، احنا فاميلي مع جامعة الكويت، بنشتغل مع جامعة الكويت وبنورد لهم برامج بقالنا أكتر من 10 سنوات. وبروجرام Spss هنا في الجامعة من البروجرامز الأساسية اللي بنستخدمها دايماً في كل التخصصات. أنا مش عاوز waste your time أضيع وقتكم. Let's start with John. John, our data analyst. الكلمة للدكتور سليمان. تفضل.
Thank you, everyone. Welcome to this workshop. I would like to thank everybody for attending, Smart Vision for creating this, and Da'am al-Fani for doing these kind of workshops. And John, welcome to Kuwait. First time in Kuwait?
No,
Okay.
third time.
Okay, third time. So personally, I've used SAS maybe in the late 1990s, and it was quite a big difference when I switched to SPSS.
Okay.
And I'm really looking forward to see, especially with Amos using for structural equation modeling and these things, and AI. So I'd like to welcome you. It would be very interesting.
You have a great knowledge. I didn't expect it much.
Okay, so I'm looking forward to hearing you. Unfortunately, I'll only be here for the first 15 minutes, but I'm sure Dr. Zeynep will let me know on what else is happening.
Okay.
Thank you.
Thank you very much. Good morning, everybody. Welcome from me. I'm John McConnell. I'm based in London. I run the services team for Smart Vision in Europe, and I work very closely with Mr. Zodi in the region here as well. I've also used SAS, but I don't say that too often because my background is more SPSS, okay. But we still use SAS. Can I just ask, just before we start, how many people here today use SPSS? Some do, some don't. Yeah. How many people use Python? Okay. And R? Anybody use R? A few people. Okay. Some people have the full set. That's great. That's great to hear. Thank you. So today, what I want to do is, first of all, I'm just going to talk a little bit about Amos, because I believe there are some people here perhaps and online who, some people use Amos and some people are thinking about using Amos. So I just want to give you a bit of an introduction to what Amos is about, as well as what's new in Amos and what's been developed more recently. So I'm going to start with that. And then I'm going to sort of take you on a little bit of a journey. Everything is a journey these days. We have patient journeys, customer journeys. Everything is a journey. So this is a statistical journey into machine learning and into AI. And to some extent, it covers my experience in the last so many years, I would say, and I suspect many of you in this room as well. Okay, let's start by talking about Amos. Now, Amos is interesting because you have SPSS, and we're going to look at two versions of SPSS today, and we'll look at some Python and some other things. And Amos sort of stands alongside and integrates data back and forth from SPSS. And fundamentally, at the core, it does a kind of regression. So you may ask yourselves, well, why would I need to use Amos when I have SPSS or SAS, or I can do regression in Python or R or whatever it is? And the clue is that Amos does something that the other tools don't do. It does structural equation modeling. So it does a more comprehensive regression, you might say, fundamentally. It isn't just a simple regression with, say, main effects and dependent variables. It's also, thank you, perfect. It is essentially a regression structure. The word structure represents a kind of regression system, and we'll see some visualizations of what those regression systems look like. It's also a little bit of factor analysis along the way. Again, if you're not familiar with AMOS, but you're familiar with doing factor analysis in say, SPSS or SAS or somewhere else, then it brings the two things together. So it brings observed and unobserved variables into the same system, the same modeling system, you might say. It also does, and we'll see the visualizations of this shortly, what's called path analysis. And we can do confirmatory factor analysis. So we might explore and find factors inside SPSS, let's say, and then we might test them and confirm them within a broader structure within AMOS. So it is these advanced capabilities that AMOS brings together into one place that makes it special and different, we would say, and more robust and more accurate and more complete. So the way that it handles missing values, the way that it allows you to do bootstrapping, the way that it takes you beyond traditional regression, and we'll visualize what that looks like shortly, is the key to what makes AMOS different. And also the modeling of latent variables. Now, latent variables may be variables that we find from a factor analysis, an exploratory factor analysis, let's say, or they may be latent variables that we hypothesize about because we know within a particular system latent variables exist. And these are particularly prevalent in the social sciences. So I assume do we have some social scientists here today? Some people who do marketing research and so on. They're not exclusively there, thank you, but they're typical in and around those schools and those disciplines. So things like intelligence, which isn't something we can necessarily measure directly, is clearly something that is at play whenever we look at, say, student performance, for example. So what does it look like? Actually, let me just show you AMOS and I'll build this particular example so you can get a sense of what AMOS is about. Just in terms of questions, by the way, I'll probably stop after each section. Just we have 3 sections, really. Maybe I'll stop for questions at that time, if that's okay. So here's AMOS, and one of the nice things about AMOS is that it's a very visual interface. So we draw our structures, we draw the path analysis. And the way that we do that, I'm just going to create a relatively simple structure.
I haven't used it in maybe 10 years, but I see the interface hasn't changed much.
It hasn't changed much. It has improved in little ways, I would say. Yeah. But it's a bit like, I'll show you SPSS Modeler later. Did you ever use SPSS Modeler? No. It's a very similar concept. It's drawing the analysis and visual, we call it visual statistics, visual data mining, and visual data science, I mean. So I'm just going to create 3, sorry, get the right, 3 independent variables, and I'm going to create 1. So this is a relatively simple, we'll see some more complex paths later, but this is a relatively simple one. And then I'm going to drop, it's a relatively small data set, I'm going to drop performance as the target, as our dependent variable, and then knowledge, value, and satisfaction as our predictors. So it looks like we're building a regression with dependents, with 1 dependent and some independents. I'm now going to draw the relationships. So I'm going to say knowledge drives performance, value drives performance, so does satisfaction. So far, so good. We could do this in SPSS straight. What we can't do in SPSS, or not very easily, is build the covariances that exist between the independent variables. And again, within AMOS, we can do this visually. So we can draw the relationship between value and knowledge, between satisfaction and value, and between satisfaction and knowledge. Now we can run. Oh, I've got something wrong with my constraints. So I'm going to very quickly run to my built model. Like so. So what we see, first of all, again, if you're familiar with regression, these are the b-values in regression. These are the unstandardized estimates. So you can start to get a sense that there's some covariance going on between value and knowledge. You can see it looks like, and we can't see necessarily yet because we have to understand the scales that are at play, but it looks like knowledge is a stronger driver of performance. It has a stronger relationship with performance, followed by value, followed by satisfaction. But to be able to see that more clearly, just as we would in a regression, we need to move to the standardized view. And there are a couple of things we see here. First of all, we see this value here is effectively the R squared, which is one of the values that we look at first in a regression to see how good the fit is. Not bad. 0.4, 40% of the variance is explained by this model. What we see more clearly now, though, is that knowledge is a clearly stronger driver of performance than value. But those two together are the two drivers, the two independent variables that are influencing, if you like, the performance. Satisfaction, less so. So it's 0.1 compared with 0.35 compared with 0.4. And we do see that there is covariance at play. So we can see knowledge and value. And again, we might start to hypothesize these things. They are clearly related together. So this is something that we wouldn't typically see even in a simple SPSS model. It's hidden away from us. So as we said, the R squared is 0.4. We talked about the strongest covariance. We said knowledge is the strongest driver of performance, as well as that feeling of self-value. When we look down at the coefficients, what we see is that this satisfaction at 0.1 actually is not statistically significant. So remember, we always look for the magic number 0.05, and if a number is above 0.05 in SPSS. SPSS tends to call it the sig value. Maybe we should call it the p-value more broadly. Then we say it's not significant at the 95% level. Okay. Now, the thing about AMOS is it doesn't stop there. It doesn't just give us a short list of diagnostics, model performance diagnostics and other outputs in the way that SPSS does. It gives us much more detail, much more information. So we can start to assess, first of all, is this a good model or not? So these are that, we do a lot of project work with AMOS, and this is our checklist. I'm not saying that this is exactly how you should look at it, because there's lots of literature around to talk about different ways to interpret AMOS models. But we tend to look at the C-min over diff, which is this number here, and we have thresholds that tell us whether we think the model is acceptable or reasonable. Actually, in this example, we're above the threshold, so that's a bad start. But everything else falls pretty much into line. So we look at the NFI, if it's greater than 0.9, greater than 0.95, sorry, that's excellent. The CFI, if that's greater than 0.95, that's excellent too. The root mean square error, the RMSEA, SEA, again, that's down about 0.032, so that's pretty good. The AIC, the Akiki information criteria, and this is an interesting one now because we're going to talk about machine learning later. And I'm going to make a statement, which I'll maybe come back to, that a lot of machine learning is about automating a lot of the processes that we're looking at here, where we go through, as statisticians, as analysts, as researchers, we look at the statistics and we make decisions based upon whether they're significant or how strong they are. So I'll come back to that shortly when we start to move into machine learning. But the AIC, actually, it's a number that it's only really useful in a relative sense. So when we build multiple models, we can compare the AICs and we can see which is the better model. Okay. So far, relatively simple path analyses. I'm going to, first of all, give you a conceptual path analysis to start with, a design that starts to bring in that next level, so the latent variables that we talked about. So in the last example, very simple, we just looked at observed independent variables. Here, we have some observed variables, 2 psychological tests, an IQ test, years in education, time spent training, and we have latent variables that capture those. Only 2 in each, but they capture what it means when we put them together. So this is about how social, we're trying to measure how social the respondent is in this example. Here we're trying to measure their intellect. Obviously the IQ is part of it. Years in education is a proxy potentially for how intelligent you are, what your intellect is. And then motivation is how much time you spend doing things in this example. So how long do you spend training? How long do you spend doing your job, working? So there we have the latent variables. And we're saying, you know, they feed into here. So they're drivers, if you like, of these constructs, these latent variables. Then we have another latent variable. Latents are circles or ovals, and observed values are, measured values are rectangles, typically. So we have the 3 latent variables come together to give us a single latent variable, which is the performance in the job. So we look to measure that relationship. Again, we may not have tested this yet. We're hypothesizing it, we draw it, and hypothesizing is something that's really important, of course, in statistics. And then we say, well, we think job performance then drives these 3 measures. And those are client satisfaction. So in this job, you have customers. The customers are surveyed, and they tell you how satisfied they are with your performance. What your supervisor thinks. So what does your manager think about your performance? How does he or she score you? And then how good you are at completing projects and delivering projects. This feels a little bit like my life, if I'm honest. I don't know if anybody did this yet for me. But, now, one other thing that's really different here, first of all, you know, this would be tough to do in SPSS because you would be running, or SAS, you would be running separate analyses and trying to stitch them together. Here, it's in one place. Is we have 3 dependent variables all being analyzed at the same time. And I think for me that emphasizes the difference in AMOS, that you can do that. You cannot do that simply in another SPSS package. If we look at the outputs, we can start to see, if I start from the right-hand side, because we're interested in what's driving these 3 dependent variables at the end, you can see job performance is equally weighted on the satisfaction of the supervisor and on project completion. Again, which is intuitively correct, I would say. It's weaker when it comes to client satisfaction. So the fact that I'm good at my job doesn't necessarily mean my customers are satisfied with me. There are other things at play there, maybe. Just the way I am as somebody who communicates perhaps with the customer, how often I communicate. So you start to think of the other factors that we perhaps need to add into here to explain client satisfaction better. And I'll show you, I'm just going to show you one more, which might be slightly hard to see, but you'll be able to see it more clearly. Yes, it's hard to see. You'll see it more clearly when you see the slides. But this is a piece of work we did recently. We have a colleague who spends a lot of her time doing SEM. And this was for a fairly major global games platform. And they had an internal measure of how satisfied they were with the providers of games, you should say, to their platform. But it was a complicated picture. And they had on the outside, they have lots of observed variables. Some of them come from surveys. Some of them come from internal KPIs and metrics and all those things. And they link in and they come together in different sets to create 13 latent variables, 13 unobserved variables. So things like growth, future-proof, work experience, ease, enable success. And then there's a second stage where we bring together the latent variables and sometimes the original observed variables into a second step of latent variables. So things like values, solutions you can rely on, transparency, and so on and so forth. I should say this is a good example also of, this was based on a theoretical model, which is often the way that you work within AMOS. You know, you can start with something that came from a paper or a piece of research, and you can look to apply that into your study. And then the the final satisfaction was based upon the second set of latent variables. So that's, I want to say that's a particularly complex path analysis. I'm not suggesting you would necessarily do that, especially if you're new to AMOS, but it's something you can build towards. And it just demonstrates the level of analysis that AMOS can do that is pretty unique in terms of an approach. So that's really about visualizing structural equation modeling. Now, one of the questions we always ask ourselves with, and Mr. Zodi will confirm this, with software that IBM acquire is, will IBM invest in that software to develop it? Will they take it to the cloud? A lot of the software we work with today is in the cloud. The good news is, these are the recent improvements within AMOS. AMOS is being developed. The user interface, we just talked about a little bit. There have been some improvements there. It hasn't radically changed, but it's very similar. The main changes recently are, we'll talk a little bit about Bayesian through today, but Bayesian analysis was added in and then enhanced, and it allows us to produce models, particularly when we have non-continuous data. So when maybe we have ordinal data or sometimes nominal data, it depends. Latent class analysis. Can I just ask you, raise your hand, has anybody done latent class analysis at all? Okay, not many, no. It's a form of segmentation, let's say. But what latent class can do within an AMOS analysis is it can identify underlying, that word latent again, classes or segments. So what we might find is, we have our, I'll just quickly go back. We have our simple picture of performance here, which is at the sample level. So this is the whole study or everybody in the university or whatever it is. But if we run a latent class analysis on it, we might find that there are 3 or 4 different segments underneath. And they're groups that behave differently, and they will have different path diagrams. So it allows us to look at, it's based upon the path diagram. It's to say, look, we can deconstruct the path diagram and find those underlying segments. Deseparation analysis is relatively new. It allows us to analyze the differences between dependent and independent, conditional independencies and dependencies within the path diagram itself. There were a few R users here, not too many, but there is R integration now. AMOS has its own language as well, which is a programming language which sits underneath a little bit like SAS or SPSS. But you can control AMOS from R these days. And there are also interfaces to Visual C# and Visual Basic and so on. So I was going to take a pause there. That's really what I wanted to say about AMOS. Has anybody got any questions about any of that so far? By the way, you have my email. If you have questions beyond the session, then please send me the email, and I'll be very happy to answer anything that you need to ask. Okay. Yes.
Yeah, my question is not about the statistical or technical information that you presented, but about actually, is this tool, AMOS, is available for us to use?
موجودة SPSS version 29 والأموس version 29 already موجود.
Okay, and then how can we get it, utilize it?
Thank you. When you use it, you ask yourself, why did I just do regression? It's like, why did I? It just has the complete picture. Yeah. So I'm going to. We talked about the journey, and here we're going to talk about 3 schools, if you like: statistics, machine learning, and artificial intelligence. And we'll start to walk through. We'll talk a little bit about statistics. I'm probably going to be telling you things you already know to begin with, just to remind you some things, so that we can then understand how statistics is important and how it's used as we go further. Let's start with statistics. So again, just at a very high level, there are two schools of statistics, which I'm sure many of you are aware of. When you use SPSS or SAS, Python, R, usually you're working with what we call traditional or frequentist statistics. And that was arguably invented or pioneered by a gentleman called Ronald Fisher in the 19th century. But before that, there was Bayesian statistics, named after the man himself, Thomas Bayes, who was around in the 18th century, as it happens. So he was a little bit earlier. And in some ways, they're sort of two different sides of the coin. You know, they look at statistics and solving statistical problems, not in opposite ways, but in sort of fundamentally different ways, if you like. If we start here, and this is the way that we're going to be looking at most of our analyses as we go through and we talk about statistics. Traditional statistics, frequentist, is saying we build probability based upon our observations, based upon what we see. So if my football team wins 50 out of 100 games, then it's a pretty good estimate to say, you know, the chances they'll win the next game is 0.5. Okay, there's other things that come into play, as we know. And statistics themselves are the estimates of parameters. The parameters are the actual real value that exists in the population, as we often say. So with statistics, we're trying to, in traditional statistics, we're using a statistic to estimate a parameter. That's really the basis of it. We rarely talk about parameters. We usually just talk about statistics, but that's the basis of it. And the whole idea is that we can have samples. And of course, so much of this is about the history of data. And we are where we are today with AI and everything else we're going to talk about, largely because we have so much data now, so much data is collected. As you go back in time, less data is collected. So in order to try and understand what a parameter is, what is the real value of income, salary, let's say, in a particular country. Previously, we could only take a sample. That may be a few hundreds or a few thousands, and the real value is in the millions. That the parameter value is out there, but it's based upon millions. So we use inference, statistical inference, and we use known distributions, and we use confidence intervals. We'll see a little bit of that shortly, to see what is our estimate, what is our statistic, and how confident are we about it. Bayesian, on the other hand, turns that around to a certain extent. It says, I believe I know what that value is. I know that let's say the probability measure. And parameters are not fixed values out there. They're random values. They move around. So conceptually, it's a different way of looking at it. And then there is something called Bayes' theorem, and I should have put in the formula here, but I'm sure you've all seen it, which talks about prior and posterior probabilities. And it's really, the fundamental idea of Bayesian is we start with knowledge, and we have a good estimation, hypothesis of what a particular value is. And then we update that with the data. So the data provides more evidence, if you like. So here, most of what we do, I think, in statistics is still here. We start with the data. Here, we start with something else. We start with a hypothesis almost, if you like. That makes sense. Now, I'm mentioning this because what's interesting is we'll mainly focus here because that's where most statistical effort is. But what we're seeing as we go into machine learning and AI is that the Bayesian school or the Bayesian approaches are becoming more popular and more used. So we'll talk about that as we go. So I'm going to take us into statistics first and then to take us into machine learning. I'm going to take a relatively simple case study. And we're going to start to analyze it statistically. We have customers of a bank, and we have a point in time where we know things about our customers, and we know that in the following 6 months, 3 months, a certain number of them go on to leave the bank. They churn, if you like, they exit the bank. So what we want to do is try and understand A, what is it about those that leave the bank that is different to those who stay? That's where we're going to start in the statistical way. And then further on to that, what we want to be able to do is develop a model, a predictive model, a machine learning model, or a statistical model, let's come back to that, which will predict for a given customer at a given point in time, how likely are they to leave the bank in the next 3 months. So it's a churn model, if you've heard of the concept. What we're going to say to begin with is that we have a sample of 500 customers. Not very many, but remember the point of statistical analysis is we can use statistics to make inferences about all customers, about the population, about the actual parameters. So what I'm going to do very briefly is, I've got 2 hypotheses, of course, and statistics starts with hypotheses. First of all, I'm going to say I believe that men are more likely to stay with the bank than women. I may have some subject matter expertise that makes me think that. I might also think that customers with a low credit score are more likely to leave. Again, this may be based on what we know as someone who works within the bank and works with the customers. So the way you try and answer those questions, first of all, is a statistical way. We've got 500 customers, so let's look at how we would look at that. So I'm going to open up SPSS statistics, and the first thing I'm going to do is say, sorry, what's my first one? Men are more likely to stay than women. Okay. So what I can do is I'll do this. First of all, I'll do this through a table, and then we'll do something visually. But I'm going to analyze. Let's build a table. You can use crosstabs for this. If you have custom tables, it just makes it a little easier to do. It's one of the modules. And I'm going to say exited in my columns, and I'm going to take gender as the rows, and I'm going to put in, I've been using crosstabs for years, and I always have to stop and think at this moment. Is it row percent? Is it column percent? Sometimes I just put both in and then take one out. Okay, let's run that. So remember, I know it'd be a little hard to see. It is in the presentation as well. You should see it more clearly there. But what we're hypothesizing is that men are more likely to stay than women. In other words, women are more likely to leave. And that seems to look correct. So it's saying that these are the key numbers. 32% of females leave, 17% of males leave. Not quite double, but there's a big difference there. However, we only have 500 customers. So how can we be confident that, across the bank as a whole, which has thousands and thousands of customers, that is correct? Well, this is where we use statistical theory, and we look at distributions, and we can run a statistical test based on the null hypothesis always, that there is no difference. This is always, when we do statistics, this is always like double think. We have to think, okay, our hypothesis statistically is that nothing is happening. We want to disprove that. That's always a slightly strange way of thinking about it. So if I go back to custom tables, I can put on a test statistic and say I want to compare column means. I click OK. Oh, sorry, I picked the wrong example. Column proportion, I should say. So this does a t-test, this does a z-test. We want a z-test because we have percentages. There we go. Okay, so this confirms the same numbers we saw before, but this confirms that there is this number is statistically different to this number is statistically different to that number. So. Now the next hypothesis that we had was that credit rating, customers with a lower credit score are more likely to leave. Now this is something that we can analyze visually. So if I go into the chart builder in SPSS, and I can say, I can do an error bar. My x-axis is whether they exited or not. and then my y-axis is the credit score. I'll just run that. Okay. Now what we're looking for here, again, this is about looking for statistical significance. And the points are the averages. So the average credit score for those who stay and the average credit score for those who leave. And it doesn't look very different at this view. We perhaps have to zoom in a little bit to see it. So I'm just going to go into here. What we're looking for here is to see, if you draw a line, whether what you want is the upper confidence level here to be lower than the lower confidence level here. And if that's not the case, then we accept the null hypothesis that we can't see a significant difference. And in actual fact, we can see there is a difference in the means because the circles are lower down, but the confidence intervals overlap. And when they overlap, we can't say with any degree of confidence that that is the case, that there is a difference. Okay, I'm going to flip this now and say, okay, what if we look at the same analysis, but with 10,000 customers? So almost the full customer base, let's say, at a particular point in time. So just to save us some time, I'm going to paste the syntax of that analysis. And just a note, by the way, for those of you who use Python or R and you use ggplot, ggplot is based on the grammar of graphics, which is the same graphical engine that SPSS has in it. So it's quite a flexible engine, just in the same way that it is for R or Python. And I'm going to open up a 10,000 record file, and I'm going to run the same analysis. I'm just checking that. Let me try that again. Run it against the old one. There we go. I'm just going to close that data set so there's no confusion. Run that again. Okay. So let me again zoom in on those relationships. Okay, can everybody see that a little bit better? So here what we see is the yeses, again, are their average credit rating is lower than the no's. So that confirms our hypothesis, at least in terms of the differences in value. And here what we see, it's hard to see, we'd have to zoom in even further, is just that we don't have overlap. So we would, in this case, reject the null hypothesis and say, actually, yes, there is a difference, a real difference between whether a customer is likely to leave based upon their credit score. Lower the credit score, more likely they are to leave. Okay, so we could go on, and here what we're doing is building up almost like a forensic picture of why customers are leaving. So whenever we have a dependent variable, whatever that might be, there's a great book called Predictive Analytics, by the way, by a gentleman called Eric Siegel. And the tagline is, let's predict who will buy, lie, click, or die, which is, it ends in a bad way, but all of those things are classification targets. And the approach that you would take to analyze them is essentially the same. We can start with hypotheses. Why is somebody lying? And we can start to do our detective work to try and understand it. Okay, so that's statistical analysis. It's not machine learning at the moment. And I've got some more examples of different analyses that we did in the slides, which you can take a look at on the statistical side. Now, let's move forward into what's known as, what tends to be called machine learning these days. It's data science. So, we have statisticians and we have data scientists, and we can talk about what's the difference or what's the similarity between them. There's an old joke that a data scientist is a statistician in Silicon Valley, but I wouldn't say that. So, when we do machine learning, we use, and I'm not going to spend a great deal of time, I'm just going to talk about this on the high level so I can illustrate the kinds of things that we do. But we use this model called CRISP-DM. And it allows us to do a number of things, one of which is to really structure the machine learning exercise in such a way that we're likely to get success, and also that we're likely to get agreement on what success looks like, which is another critical step in the process. There is more detailed documentation available, by the way. I will put a link onto the slides. The process starts not with any analysis, not with any data, but with a design, if you like, a setup of what is the analysis that we want to perform. What is the research or business objective that we're trying to solve? So in our example, what we want to do is to ultimately stop customers leaving. We might want to stop customers lying or clicking or whatever it is. It depends on the classification. So the point of business understanding is we all understand the objectives, the context. And that's the statisticians, the data scientists, the researchers, the business users, the database people, whoever needs to be in that group to define the context and share it and understand it. So it's usually coming together, depends on the size of the project. And one important point, and we'll come on and talk about a little bit about what each stage is, that when we're doing this, we're thinking about the final step, which is deployment. Because the whole point of doing this is to find perhaps insight or build predictive models that allow us to change something, to allow us to improve something, to fix something. So it's really important that we don't forget, when we're having this conversation at the beginning, we need to think about how are we actually going to use the results when we find them. Okay. So we might be thinking about our hypotheses. What if it turns out that the biggest driver of exiting is gender? What are we going to do about that? Is there, first of all, we probably need to understand better why women are more likely to leave than men. Maybe we have to do some research. We have to start to think about, if that is true, what is the next step? How do we use that? A key point is about agreeing success criteria. What will a good outcome look like? And here I'm going to focus on the models, the modeling side of it, so the machine learning side of it. So we build a model, and a model has a certain level of accuracy. We'll talk about that as well. So any machine learning model can be tested, and it has a certain amount of accuracy. We'll talk about how we do that. In our example, though, what the bank tells us is, in a single month, we can only communicate with 2,000 customers, maximum. So we may have 10,000, 20,000, however many. But we can only communicate with 2,000. So what the bank wants is the list of the top 2,000 customers who are most at risk. And you see this in other places. If you think about credit card fraud or insurance fraud or lots of other applications where we want to find the risk list, if you like. Then in terms of accuracy, what they're saying is we want to accurately identify within that 2,000 70% of customers who will churn. Okay, so that's our target. That's our agreed target with those who own the problem, where we as data scientists and statisticians are trying to solve the problem. And that's often a negotiation. And it's sometimes a difficult negotiation to agree, you know, is that a number we think we can achieve, you know? Is that a number that we, you know, we'll talk about lots of sources of pre-existing models later, things like Hugging Face, which we'll come back to. You know, is there evidence out there that we can build a model that's accurate enough to do this? So now we get into data understanding. Now I'll be honest with you, and I hold my hand up. I'm somebody who's done this myself sometimes. Sometimes you're in a hurry. You don't spend enough time doing this, and we do recommend, even in the world of AutoML, which we'll talk about later, we do recommend it's important to really spend time with the data, like the statistician just did, using SPSS statistics to sort of tease out those relationships. And it's important to realize that actually fundamentally a lot of what happens within data understanding, within machine learning, is statistical practice. It's using statistical method to find extreme values, unusual values, perhaps incorrect values, outliers, extremes, to find gaps, missing values, and to potentially fix the missing values. So lots of statistical algorithms allow us to fill in missing values in a very robust way. And to do some of what we already did. Let's test some hypotheses, just as we did. So we start to understand the data, and it starts to tell us what is it we want to put into the model. Now, this is an important I don't know, I was going to use the word juxtaposition, but that doesn't really say. This is an important alternative today, which I think is at the one hand powerful and then on the other hand dangerous within machine learning, that we don't do this and we allow the algorithms to do everything for us. Personally, I think there's a little bit of risk in there, but I think there's power in it as well. So we'll talk about both approaches. So think about exploratory data analysis. Think about those of you who've done EDA before, the types of analysis that John Tukey would talk about. So doing box plots to look for differences, look at extremes and outliers. So I'll show you what that looks like. So something like that, where we're looking at those who exited, and we're looking at the bank balance this time. And we can see, perhaps interestingly, that the median, so the middle of the box, in box plots, is the median. Sorry, the line is the median, I should say. Those who have a slightly higher balance are more likely to leave. So that in itself is perhaps surprising. Maybe we would have hypothesized the other way around, but perhaps it tells us something interesting. It probably tells us that's something we should worry about, because it's saying that our customers who have more money invested with us are more likely to leave. Some other examples here. Here we look at age, and you'll see there's a data audit in the slide deck that looks for this as well. And interestingly, with age, we see lots of outliers and extremes. So that might be dirty data. There might be something wrong with the way that data was collected. We need to look at that more closely. But what we also see here is, again, if you look at the median age, those who are leaving tend to be older customers as well, because they have a higher median age. They're above 40, closer to 50, whereas those who stay are below 40. Yeah. So this is relatively quick to do. You know, we can still get on and do our machine learning, but it helps us understand and inform how we do our machine learning, if you like. And it may inform other things as well. Okay. The next step is data preparation. Data engineering is most likely what it gets called today. The reason we call it engineering is because as data has grown, and data complexity has grown, and we're in the world of data lakes, no longer data warehouses, it is more of an engineering exercise than a preparation exercise. And I think it's an appropriate change in name that we talk about data preparation. Usually when we're building a model, this is where we spend more time than any of the other steps. So we're potentially cleaning data, fixing errors, sorting out missing values, looking at extreme values and so on. But very often combining data together from different sources, in a bigger project, and often creating features, as we call them, which is very much about how we make machine learning models more powerful. I'll talk about that a little bit shortly. What I'm going to do this moment is just show you, visualize how that would happen in SPSS Modeler. So SPSS Statistics is very much the statistical tool where we're doing the kind of forensic analysis, traditional statistical analysis that we talked about before. SPSS Modeler is a visual tool, not unlike AMOS, that allows us to visualize a path, a stream, an analytical flow. Can I just ask, has anybody seen SPSS Modeler before? One or two people? Yeah. Once upon a time it was called Clementine, so they changed that. Okay, so what I do here is I'm going to take the same data set we looked at, I'm going to quickly do some data understanding, and then I'm going to go on and I'm going to do some machine learning, I'm going to do some modeling. Okay. So first thing I'm going to do, and I'll explain why, is just have a look, and I didn't do it yet, I could have done it in the statistical analysis, so I'm just checking the numbers. I need to check at that point in time what the distribution is of those customers who stayed versus those customers who left. And as you might expect, fewer customers leave than stay, but it's still around 20%, 20.5% of customers who leave. So it's a significant number of customers. Now that's important when we come and look at accuracy, and I'll explain why shortly. Then we can do things in here like we can run, and I'll just run this quickly and show you, and again it's in the slides, we can run a data audit, as it's called, which is essentially doing a statistical analysis of all the variables on the file. Okay? And it's telling us things like what's the min, max, mean. It shows us the distributions. So very quickly we can just go through line by line and see if anything doesn't look right. And over here we have the quality tab, which is a bit harder to see, but it tells us, have we got unusual values, outliers or extremes. How do we define outliers or extremes? Statistically. So you either say an outlier is, I think it's 1.5 standard deviations or 1.5 interquartile ranges from either the mean or the median. An extreme would be 3 standard deviations or 3 interquartile ranges. Actually, that looks pretty good. We don't have much of a problem, apart from age again, and we visualized that. We saw that earlier, didn't we, when we ran the box plots. So maybe we need to go and look at age just to see what's going on. However, when we go back to the audit, we can see, actually, the largest value of age is 92. So it's not actually that high. You know, it is just, we've got a skewed, slightly longer tail in the distribution, probably. And again, to confirm that, we can do that using a histogram, a statistical technique, a statistical visualization. So you can kind of see what's happening. You know, you have a sort of skewed normal distribution, it's skewed to the left. So that answers the question. Okay, we've got outliers and extremes, but they look realistic because, you know, we have fewer and fewer people as you get towards 100 as customers of the bank. Okay, so far. Now, typically, we have more variables. We're reading data that hasn't been analyzed before, so we spend a lot more time doing that, and we spend a lot of time doing data preparation and fixing that. But let's do the actual core machine learning now. And in our CRISP process, there are 2 steps which are really linked together, modeling and evaluation. And modeling is where we effectively apply and tune algorithms. Machine learning algorithms. Statistical algorithms sometimes, often, and we'll do that now. And we might say, well, are we doing statistical analysis or are we doing machine learning analysis if we're running a statistical algorithm in and amongst other algorithms? I would say we're doing machine learning with statistical algorithms. And there's a certain amount here, and we'll come back to it, about what actually is machine learning, what actually is artificial intelligence. And there's no real clear definition, but most references now would say, for example, regression can be used to do machine learning. So this is one of the key ways, as well as everything we've talked about in terms of how important statistics is in understanding the data as we start to do machine learning. Statistical algorithms are now really part of machine learning. Okay. So let's take a look at that. But before we do it, the key thing here is, and this is, again, where we just need to change our mindset. If we started off as statisticians, as I did, as many of us did, you know, you think about samples, you think about assumptions, about fitting distributions, about residuals, about all the boxes you have to tick in order to do that inference from the sample statistic to the parameter. Here we stop thinking about that. And often that's a difficult concept for a statistician who's been doing that for 10 years or 20 years to take on board. Because we've got more data, fundamentally. That's part of it. But the main thing is because we test. So what we do is we take a training sample, it's called different things, but a holdout sample or a test sample or a validation sample. And we build a model on the training sample, and we hide the validation sample from it, and we say, okay, how accurate, your model's built here on the data you've seen, how accurate would you be on the data you didn't see? And the way we set that up, again, if I go back to modeler, is we create a partition using a random selection. Again, a statistical concept. So we randomly select, and you know, you can try different numbers. 80% of customers in this case to be part of the model build, and 20% to be in that test, that holdout sample that we're going to use to see how good the model really is. Okay. So I've got two models here, so two algorithms here, I should say. The first one is statistical. It's a logistic regression, and it's a logistic regression because we have a binary dependent variable, a binary classification dependent variable. Okay. And by the way, all those targets that I talked about earlier, buy, like, click or die, are all binary classifications. Lots of data mining problems are, not all of them, we'll talk about some other examples, but very often we have classification problems. There may be more than two classes. Okay. And we're just going to let that run. And at the same time, we're going to run a much more contemporary machine learning algorithm called XGBoost. How many people have heard of XGBoost? Can I just ask? One or two. Okay. XGBoost is a form of a decision tree. Well, it's more than one decision tree, it's multiple decision trees. Actually, I'm just going to very quickly show you, sorry, I forgot something. I'm just going to show you something else very quickly, and then we'll run the models. I'm going to run another decision tree called CHAID. Sorry, can I ask again how many people have heard of CHAID? Just out of curiosity. Okay, so CHAID is a machine learning algorithm. It stands for chi-squared automatic interaction detector. Chi-squared. Obviously, chi-squared is a very familiar statistical test. So you think about the testing we were just doing earlier when we were using SPSS statistics, where maybe we were looking at one test at a time. Machine learning, to a certain extent, automates that process and does thousands of tests at one time to tell us where the significance really is. Okay, so just to show you how it would work, essentially it's doing lots of crosstabs. So again, just to emphasize, machine learning method built on statistical testing.
Excuse me. Yes. Are these algorithms like built-in algorithms?
Yes.
Like within the program?
Yes. Yeah.
Okay. Can we modify the algorithms, or it's like you cannot do anything?
Some you can, and some you can't. So some are open source, and you can, and some are not, and therefore you can't. Yeah. So XGBoost, you can. CHAID, you can't. You can't in this software, but you could. I'm sure there's an open source CHAID out there. We'll talk about some open source libraries later that you can take a look at, where you start with a model and then you can adapt the algorithm. So we start with an algorithm, you can Start with the modeling and adapt the algorithm. So what we do here is we say, okay, we've seen the distribution, which is 20% churn. We can right-click and say, grow branch with custom split. And what it does is it tells us, because it runs that chi-squared statistic, that chi-squared test on all the variables, and it ranks the variables according to their significance. We could rank it based upon the chi-squared value or the significance. It's kind of just different sides of the same coin. We already tested age when we did our analysis, and we saw there was a difference there. What we didn't look at yet was the number of products. So the number of products a customer has a slightly higher significance in terms of telling us whether somebody will leave or not. This has gone from doing it in a bivariate way to effectively a multivariate way, a bit like doing a multivariate regression. So I can build that out, and I can do this interactively. Sorry. Okay. What that's telling us is, and again, it's something we've seen earlier. Remember, we had some evidence that said customers with higher balances were likely to leave, older customers, so perhaps those that are more valuable to us. Here we see customers with more than 2 products. There aren't many of them. It's only 3.5% or 3.4% of customers, but they are 84% likely to leave, compared with 20% of all customers. So that in and of itself, even before we get to build a model that will predict the risk score for every customer, is perhaps a piece of insight that we might want to take and do something with. You know, we might want to understand what are those products. You know, there are particular products that are encouraging customers to leave. What are they? And maybe again we need to talk to customers. And you can carry on from here. So we might say, okay, there's a big group here. So we're quite small here. We're down to 274 customers. We've got 3,691 customers here who have 2 products. Let's see how they split out. So again, this is using chi-squared to say I'm going to pick the strongest variable for this group, who are the customers with 2 products, to say actually what's the next best predictor. And in this case, it's age. We already saw that age is a strong predictor. The older you are, the more likely you are to churn. And what this is telling us is it's relatively marginal, but for those customers that have 2 products, they're 7.5% likely to churn. But if they're over 45, that goes up by 3 times. So they're now effectively 21, just about 21.2%. Sure. Okay. Yes.
What about the safety? Is it safe for us to have that information? Because it is online program.
Sorry, could you say?
What about the safety of the information? Sometimes we use it for very sensitive information. So is it safe?
Yes. Yeah.
There is a guarantee.
Yeah.
Because it's online.
No, it's not online. No, sorry. No. It's the data itself? No, the data is actually from an internal, it's anonymized, but it's, yeah, internal customers.
Anyone can store my information or something like that, my data.
Oh, I see.
As a researcher.
It's totally anonymized. So, and that's a very big concern that we have in everything that we do with machine learning. We'll talk a little bit about that later, but yeah, privacy is really important. So we make sure that there is no personally identifiable information in the database. And we don't need it. You know, it doesn't help us do machine learning because we're looking for patterns, not specific individual. Fraud detection is a different thing, but generally speaking, yeah. Okay. So let me run the models now. So I'm going to run, just to remind you, we're running a logistic regression, statistical algorithm, and an XG boost, which is a very unequivocally new machine learning algorithm, a powerful algorithm. Okay, and in this view, we get, so these are the algorithms, and these are the models that we produce from the algorithm. So the model is algorithm plus data. That's what gets you to a model. Okay, we got two models. How good are they? Well, let's just have a quick look inside them first. And again, this is in the notes. First of all, the logistic regression tells us what it thinks are the strongest predictors. So there's another variable here we haven't looked at yet, which tells us how active the customer is. So logistic thinks that's the strongest. Age we've seen before, that's in geography, gender, and so on. So those are the variables that it thinks are important. We go off and look at, this is a little hard to see, but if you go off and look at what the XG boost says, it says F12 here is the strongest, sorry, F16 is the strongest predictor, and F16 is their estimated salary. Okay, so they see the world differently because they are fundamentally different algorithms. We're somewhat interested in their insight, but when it comes to insight, I would always go towards the statistical analysis to give us the cleanest view of the truth. Now we can check how accurate they are by, first of all, connecting an analysis node. So this is the logistic regression. So we're interested in the testing sample. Remember, this is the 20% of customers that the algorithm did not see. And it tells us that it's getting it right 84% of the time. Is that good? Let's see. What we're more interested in, because overall accuracy is an interesting number. Sorry, did you have a question? Oh, no. Overall accuracy is an interesting number, but what we really want to do is find those customers are likely to leave. So we're perhaps more interested in this number here. When it predicts 152 out of, you add those two numbers together, it's 410. How accurate is that? That's one number we're interested in. So keep that in mind. Logistic regression gets 152, 84% and 152. XGBoost takes slightly longer to run, and that's because the data is going through a much more complicated model. It gets there. Sometimes it can take a long time. It's more accurate. It's getting 87%, 86%, let's say, and it's getting 192 of the actual levers, this example. Okay. Okay. Just conscious of time, what I'm going to do is...
We can change, excuse me, we can change the training data percentage and testing?
Yes. And actually, it's important that you do. Because, again, so much statistics is in the middle of this, but we've just taken a random sample based on a seed, based on that seed, okay? What we need to do is shuffle. So we can change the seed, or, as you say, we can change, and we can do both. We can change the partition size as well, because it is just a sample. Just like, you know, we saw the samples before where we weren't sure whether they were significantly different. It's important to retest.
We can change the weight factor for
Yes.
each samples.
Yeah, effectively that, yeah. Okay. Now I'm going to look at the accuracy in a slightly different way. Remember, we set ourselves an objective, a success criteria at the beginning to say, I'm actually going to show this in the slide, but I'll show it here first. We set ourselves a success criteria that said, the bank said, we want the top 2,000 customers most at risk. We have a 10,000 file, a file of 10,000 customers, so that's 20%. So we need to look at the top 20%. And what these lines tell us is how accurate. Remember, we saw the overall accuracy. We saw the accuracy against all levers. This tells us, in that top 2,000, how accurate are the models. And the red line is the XG boost, and the blue line is the logistic regression. Now, just a couple of observations. XG boost, very complicated algorithm, very black box. logistic regression, statistical, traditional, they're not that far away. They're not, you know, XGBoost wins, but it doesn't win by this, it wins by this, which is interesting to see. So I'm just going to cut down and say, okay. Actually, one thing I'm going to do, we're just coming up to sort of the end of this part of the session, but I'm just going to run over here. I've also got a deep learning neural network that I'd already set it up, and it's in a Python notebook. So this is the third algorithm that we're going to try, and I'm just going to start that running. Oh, what did I do wrong? Okay, maybe I think my my notebook's timed out. There we go. Okay, but there we see. Okay, I'll come back to that. Okay, so what this is telling us is, at that 20% level, I know it's hard to see, you should see it in the slides, the accuracy is 58%. Remember, we set ourselves a target of 70%, so that was the target that we'd agreed, that in that 2,000 top 20% of customers, we wanted an accuracy of 70%. We haven't done it yet with the logistic regression. Nor have we done it with the XGBoost, but it's getting closer. It's up around 63%. So it's getting closer to that 70% target that we set ourselves. Okay. The other indicator that we talked about is this number here, which tells us overall what accuracy percentage do we get on the churners. And logistic regression was getting 37%. XGBoost is getting 47%, and the curve we just looked at for the deep learning neural network actually is slightly behind the logistic regression at 29%. Okay, so let's just take a pause and think about that. I think conceptually, we think about statistical analysis, statistical algorithms being simpler. We think about XGBoost being much more complex and powerful, and we certainly think about deep learning algorithms as even more powerful because they can do so many clever things that we know about and we hear about today. Generally speaking, that's true, but it does depend on the application, and it does depend on the context. And what you'll find, and the reason that we still need to involve statistical algorithms is sometimes statistical algorithms will beat the other algorithms. It depends on the data, depends on the setup, the example. My argument here would be the deep learning network doesn't do as well as we might expect it to because it's set up for much more complex data. We'll talk about it later. It's set up to do image recognition and to feed generative AI models and to do all of that sort of stuff. So it's perhaps not something that we expect to do particularly well in this situation. The final thing I'm just going to say on this section, and then we can pause, is the importance of deployment. When we get to the point where we've got a good enough model, we might decide to deploy it in lots of different ways. We might want to put it into systems, into IT technical systems. In some cases, we might want to put it into Excel. I've just had an example recently where we built quite a complicated time series model to predict something for a bank in the UK, but it was too complex and we couldn't embed it in Excel, and they wanted to use it in Excel. So now we have a statistical model which wasn't quite as accurate, but that's the model which we can easily embed into Excel. I'm going to take a pause there. Did you have a break?
Can we have like a break for 10 minutes?
So we'll reconvene.
Yeah, everything is clear, or it's deep technical? Everyone can understand what's going on, or?
Okay. The next section is less technical as well. So, okay, should we start again at
10 minutes?
10 minutes, yeah? 11:30? Thanks. thank you, everybody. What we're going to do now is move more into AI. So we very much talked about machine learning and the strong link with statistics. We started to look at what deep learning can do for our case study, our problem predicting customers. Now we're really moving into the world of deep learning and the world of machine learning meets artificial intelligence. We've all probably had our ChatGPT moment in the last 12 months or 18 months where suddenly you asked ChatGPT something and you couldn't believe the answer. I mean, the whole world is going through something. It's incredible. So what I want to do is here sort of illustrate, and everybody is learning at the same time, by the way. So what I want to illustrate is some of the things that we've been involved in and the things that we think you can potentially use in the work that you do. And just to give you some sense of just the scale of what's out there. So here I asked ChatGPT to give me two images, one to represent machine learning and one to represent artificial intelligence, slightly out of line. And this is what ChatGPT came up with. By the way, notice I said please. How many people say please and thank you to ChatGPT? But it's an important point. It is an important point.
Is it affecting the result?
Well, it may affect the future. Anyway, let's come back. Yeah, so in some ways I like this. First of all, I wanted to say there is no clear definition of where ML stops and AI begins. Okay, there's no one agreement. In the Financial Times, only 2 weeks ago, the Financial Times described machine learning as a subset of AI that uses statistical analysis, explicitly statistical analysis. Okay, we can think about whether that's true, but there is definitely a perception of the importance of statistics in and around machine learning. I don't think we should get hung up on it. It's not that important. I think we know when we're working with AI, ChatGPT is AI. I don't think we can question that. So my feeling is, and it's maybe too simplistic, machine learning, deep learning and some other sophisticated algorithms build the models, and when they're deployed, we talk about deploying the model and we interact with them in various ways, that is doing the AI. ML is in a sense creating the AI, is how I like to think of it. It doesn't entirely matter. I'm going to come back to this at the end. I am going to aim to finish about midday. So I just want to probably go through some of these slides a little quicker, so do stop me if there's anything you want to ask. But this is one view of the history of how we got to Gen AI. And it starts off with statistical analysis. And then, according to this is a German doctor, Dr. Frank, who is, we'll talk about something later, which is linked to Amos, so we'll talk about that later. But he says, okay, artificial intelligence sort of started around 1995 with neural networks, really. In SPSS, we had a neural network back in 1993. It was a difficult sell. The statisticians did not like it. Now the statisticians embrace it. Then deep learning came around about 2010, and then about 3-4 years ago, the whole generative AI thing started. And he's just saying, let's call it all AI. From this moment onwards, let's just say it's AI and be done with it. So as we said, often you've got deep learning algorithms behind the scenes, and they create what are known as foundation models. So the model that we just created that had 63% accuracy was a custom model, a completely new model. And lots of the work that we do is about building new models, or historically has been. Now we're into the world of, the first question you ask yourself is there a foundation model I can use? About, I think the question you asked earlier, is there an algorithm I can take and adapt and reuse? And so there are lots of foundation models out there, and they typically do things like natural language processing, understanding the spoken word across all the languages. And that's the great thing now. We're not restricted to just English. We can do things in Arabic, Chinese, Japanese, and so on. They can generate code for us. They can interpret audio and music. They can make audio and music. They can understand images, videos, and obviously they can talk to us. We can do dialogue. We can dialogue with them. We can talk to them. specifically, as practitioners, I think it starts with for us with not building models to use for other things, but just using ChatGPT in our day-to-day, in the things that in the jobs that we need to do and the problems we need to solve. So it can answer methodological questions. How do you do this? How would you do that? It can write code for us. And I think that was my first GPT moment when I asked it to write a program for me. It probably saved me 2 days. It was just incredible. And do all that text image analysis that we talked about. It can summarize things, it can summarize output, and it can summarize data. We ran a conference 2 weeks ago. I did the write-up for the conference. I gave it to ChatGPT. It's now much better because ChatGPT improves things. So it's a tool potentially for what we do. And let's come back and talk about that. But to get the tool, to make the tool more efficient for us, either as ourselves communicating with the tool, with any generative AI, I should say, whether that's Gemini or ChatGPT or Llama or any of the others, the Meta, will come back to me. We need to ask the question in the right way. And technically that's known as prompt design or prompt engineering these days. So if we have systems that are talking to generative AI, we need to teach those systems to ask the right question in the right way, to do the prompt engineering in the right way. I won't dwell on this, but there are a number of methodologies out there that, frameworks, if you like, that talk about how to do good prompt engineering. And you can see there are different ones. They all have acronyms: create, care, race, and so on. But they almost all start with, tell ChatGPT who you are. And then, for example, what is it you want to do? So there's a consensus, but actually it's worth trying these because you do tend to find you'll get better. Saying please probably helps, but you will get better results out of ChatGPT if you start to follow some of those principles. So here's an example. I had a problem, a statistical problem, that I think I know the answer to this. I've done this before. It's not just a simple confidence interval. It's a confidence interval based upon different samples and averaging across different subgroups. Some of the subgroups are independent, some of them are not. So I literally asked ChatGPT, how do you do this? And there it was. Of course, there's a risk. That's the one thing we have to bear in mind, because ChatGPT doesn't always get it right. So this was a piece of work that needed to be published, but at least it got me to the point of, okay, I know what I need to check now. I can check that those numbers make sense and so on. And it gave me Python code to run it. Now this is a really interesting question that I think we all need to think about a little bit. I've been involved in a lot of AI conferences where people are genuinely worried that they might lose their jobs because AI is coming and AI is doing things that we do. Now there's a way of thinking. This is a piece of sort of theoretical stuff from Giles Howell, who talked about AI a number of years ago and said the conservative view is we just say it's a lot of what it says is wrong. They're not co-workers. It's a tool. Let's just put it back in its box, let's say. Then there's the fictionalist view. It says it is pretense. Of course, AI is not a living. AIs are not living people, but they can still be useful and meaningful if we think of them as teammates. So in terms of how perhaps we get the best out of AI, it's perhaps better not to think of them as a tool like Excel, for example, but to think of them more as a co-worker with whom you can start to build up a dialogue, a way of talking and a way of getting the best out of the tools. Sorry, there is a third view, which is the really pessimistic view, that these are agents that are going to do more damage than good. And this is something, obviously, that the inventors of AI are concerned about this, so we need to be mindful of that. So you either see it as a tool, and you treat it as a tool, and you see, you think you can get what you need out of it if you use it in a very functional way, or you can think of it more as AI as part of a team, as part of one of your teammates. And this is an interesting. I asked the question about do you say please and thank you deliberately. I tend to. I again, because I think I'm personalizing, I can't say that word, anthropomorphizing. But this is based upon some survey a survey we worked on recently. It's a qualitative survey, so it's a focus group, and the focus group is undertaken by AI. Barry is an AI, generative AI tool, which is linked to ChatGPT, but asks contextual questions. And the responses we get back, there was no reason that the respondent should say thank you to the AI, but they did. There's nothing else going on in there. Or in German, you're welcome, or whatever Gurnemese, I can't remember. But then it goes a stage further. Some participants in the in the session actually wrote to the AI after the session, and somebody sent pictures of their holiday. I mean, but you see what I mean? There is this kind of interesting relationship that's going on. So we know people in clinical psychology who, we know clinical psychologists who are testing AI to do sessions, to do therapy sessions, because some people would prefer to talk to the AI instead of a real person. So I think it's really important when we start to use it to think about actually how can we get the best out of it. And perhaps if we do think of it almost as a person and start to develop the conversation, which if you think of it as a purely practical thing, if you're starting to understand the language that the AI understands and just work better with that tool, then the results will be potentially better. So moving way back from generative, but still around deep learning at the moment. So we work with a few tools that are based on deep learning networks. This is a recursive neural net. It's something called Phoebe, and it does, first of all, it captures voice, it asks questions, it gets the responses back, it does translations, and then it does emotional analysis, emotion detection. So I'll just play a couple of these so you can see what happens. So this is a respondent in the UK talking about food that he liked or didn't like as a child. Should come through. Try again. Oh, it stopped working. It was working before. So you see the emotion. So you can see it's processing the tone of voice as we go through. This is a very positive response, talking about food he loved as a child. So it's strong, it's happy, sometimes it's calm. It's like he's gone back into a relaxing moment in his mind. And then the same respondent talking about a negative experience. So more negative, anxious. Oh. Okay, so just a glimpse, but you can see that again, the AI this is all about voice recognition. It's understanding the sentiment within the voice. And of course, there's a massive training set behind this. And it's also contextual. You know, if you're asking people about products that they like, or you're asking them about, particularly, for example, in medicine, about their experience with different drugs or the experience within the hospital, then you have to have a different training set to capture the different types of emotion that you see there. I'll skip through these. I want to perhaps leave you some references to take a look at. Some of these I think you might know already. I assume, have people heard of Kaggle? So Kaggle is a platform where you can compete to build models. So you can build your own, start with foundation models, and often it's about good causes, so, you know, trying to find cures for diseases and so on. We're currently involved in a project where we're trying to find new treatments for cancer and for TB and some other terrible diseases. Something I really would recommend you take a look at is something called Hugging Face, and this is definitely back to algorithms you can take and adapt at the source code level. So I assume everybody is familiar with GitHub, which is a bit of a sort of technical platform where people post code. This is, in a sense, like GitHub. It's all open source, but it's all ML and AI. And there's lots of foundation models in there, and it's just a collection. The way that it's configured is really, really good. So, for example, you've got 746,000 pre-built foundation models that you can take and adapt, and it's a website so you can search them. So, you know, if you want to understand teachers' responses to English language questions, then you know you can start to look for language models and so on and so forth. And it's categorized into those different AI deep learning groups. And if I just resorted it and said, okay, which model has been downloaded the most? And it's one from MIT. It's been downloaded 745 million times. So it's almost like we're getting into the realms of Facebook and YouTube, and you know the participation and the community that exists in other social media. Okay, I'll skip over this, but Hugging Face, we use Amazon SageMaker, Amazon Web Services a lot for the work that we do, and a lot of those algorithms are available on Amazon. And this is an example of a chatbot that our colleagues have produced for our own language model, which is about Smart Vision as a company. It's multilingual. It can be voice-driven as well as text-driven. And it supports Arabic. So this is an implementation of it for a textile company, a global textile company, Shatta, that some of you may know about. So it works in Arabic as well. And again, a little bit technical again. This is an example, and we can go into more detail if anybody's interested, of something that's called a retrieval augmented generation, a RAG model, as it's known. And what it does, it starts with text, it builds vectors, and then it uses the same LLM approach that ChatGPT and Claude and so on use to, you know, in a very specific contextual version, create that generative AI prompt and setup. Just in the interest of time, I'll just explain what this is, but again, you'll have the slides, and this explains how we have a big problem in surveys when we're surveying people now, because around the world, people have answered too many surveys, they're tired, they're not responsive. There's a lot of survey fraud out there, which some of you may know about. Wherever there's somebody can make some money, there's fraud. So there's all sorts of issues. So one way we can improve upon that is to put AI into more surveys. So there's something called Inca Smart Pro, which we work with, and the concept is normal surveys are very one way. You know, we're just answering questions. Any AI that goes into a survey can make a conversation happen. So we can make conversational participants that have a two-way conversation, a little bit like the examples we saw earlier with the respondents in the call group talking to Barry. So the way that it works, again, often we'll have an open-ended question on a survey, and we'll get a response. The AI looks at the response and asks at least one or more follow-up questions, so the conversation happens within the survey. Okay, there's some more examples. It can also be used to detect fraudulent data. Let that build through, and so on. For a lot of the work we do, we're doing things like the classification model we looked at earlier. Maybe we're trying to do predictions of real values, like how much will somebody spend, or how many calls will I get to the customer service desk today. There is a new class of models. We haven't had a chance to test them yet that are doing time series forecasting. There are three in particular. There's something called Time GPT. There's Amazon Chronos from Amazon. And there's something called Tide, an independent one. They do something called zero-shot inferences. I don't know if anybody's ever heard of them, but it's a relatively new concept. The idea is that they can predict values in the future that haven't been seen in the past. Extrapolation, as we used to say in the statistical sense, which we always said, never do extrapolation, always do interpolation. Okay. Final thing I'm going to say, I'm just going to show you one thing that connects back to where we started, really, with Amos. again, I'll keep this relatively brief, but generative AI, there's something called the Gartner hype cycle. I don't know if anybody's seen it, but it's all about new technology. And what it says is, at a certain point, everybody's hyped up about how great it is, and then they find out it's not as great as they thought. So we go into what we call the trough of disillusionment. They're saying Gen AI is up here, which it probably is, but I don't think it's going to do this. It's so different to any other technology we've ever seen. But what I wanted to point out is there are three AIs on the rise. ARTRISM is all about AI in an ethical way. So somebody was talking about privacy before. So it's AI to do to almost police itself, or to have a framework with which we can police. Neurosymbolic AI is a variation on just doing better analysis of speech. And there's causal AI, which is the thing I'm going to finish on, because it's relatively new. Excuse me. It's on the Gartner cycle, and it's essentially a lot like AMOS, but it's doing it with deep neural networks. And the idea is it can help us detect all the bad things that happen, like multicollinearity, spot indirect effects in those path diagrams that we were looking at with AMOS. It can identify confounders, and it can identify causality, which is like a bit of a holy grail. What is causing what? You know, the whole correlation versus causation discussion. So I haven't tried it yet, so I can't speak for it. We're about to start testing it on some projects. Okay. So that was a little bit of a whistle stop. But just to sort of summarize, I think, what we've talked about in that final session, but also today, statistics is very much alive and kicking. There are many areas where you can only use statistics because you only have sample data, clinical trials, for example. So you can, there are very specific areas where statistics is still there. But it is central in a lot of machine learning, as we saw, either as an algorithm or as part of the machine learning process. Of course, this AI, the generative AI revolution is arguably as big as the internet, if not bigger. So we're still discovering. So we're all on a journey of discovery, even those who've been working in this area for some time. We do feel that the way to get the best out of AI is to think of AI as not somebody who will take our job away, but somebody we can work with to take away some of our job so we can do the more interesting parts of our job. So it's very good at summarizing. It's not good at making recommendations, particularly at the moment. And there are so many foundational models out there that we really need to start to look at the potential to use those more. So I think the final point from me, and I'll take some questions, is that at the moment it doesn't look like AI will replace us. Well, let's wait and see. Okay. Any questions just as we come to the hour? Okay, well, thank you very much, everybody. My email is here. I know one or two people have already taken it. So if you have any follow-up questions following the session, then please do get in touch, and I'll get back to you. Thank you very much. Thanks.
Thanks, John. Thanks for everyone who attended. I would like to take the chance to thank Mrs. Iman for arranging this with her team, Mrs. Ahmed, that is supporting us for all the previous year. With Dr. Sliman, he have data and AI knowledge, which I didn't imagine, I don't know. And to sum up, the core of Gen AI and artificial intelligence is data, and that's what we do, and statistics is the core of the analytics. That's already what we do. Kuwait University is one of the leaders in technology when it comes to artificial intelligence nowadays in the region. Thanks for everyone, and we hope we'll help you with a lot of new informations. Looking forward to see more sessions when it comes to data and AI and Gen AI for more workshops going forward, inshallah. Thank you.
Thank you.
المشاركة الفعالة